So now we'll dig deeper into the topic of probability. Assuming that you have understood the prerequisites like set theory, combinatorics, and then we also introduced what probability means and how is it a framework to handle uncertainty. Now we'll deal into this framework, and we'll see how this framework helps us to quantify this uncertainty. But some warning, some word of caution I should like to give, and these things should be kept actually in mind while you solve any problem. The first thing that you have seen, because we did Monty Hall problem, we did birthday paradox. So in all of these things, what we saw is probability is counterintuitive. So probability is counterintuitive. Because of this, you should not lose your common sense. So if you see, oh my god, probability is counterintuitive, so whatever I feel, that would not be right, so you lose your common sense. So as a result of this, you should not lose your common sense. Keep your common sense intact, but sometimes what you will feel is, maybe most of the times in probability, whatever the intuition is, you will feel that reverse is happening. So in probability, intuition won't help you that much, but still I'm giving this word of caution that you should not lose your common sense. You should not stop using your common sense everywhere, because we have seen problems like Monty Hall problem, then we saw birthday paradox, and you saw how counterintuitive they were. Okay, but at least because of a result of that, if somebody says anything about probability, so you should not lose your common sense and say, oh, my common sense is not good in probability, or let's suppose I should not think intuitively, whatever comes to my intuition, I should do the reverse of that. That should not happen. You should at least have some faith in your common sense, but probability basically will tell you why was your intuition wrong, and it will try to correct the intuition. And once you do enough practice, that's what I said, once you do enough practice, and after that you learn a lot of methodology to see things, or you learn a lot of different perspectives to look at these things, so you will probably develop a better intuition for probability things. Okay, let's now go into the details of probability. The first thing we'll define is an experiment. So what I said in mathematics, we'll put the lingo first, because consider this mathematics as a language. So in this language, we should know the words that we are going to use. So anytime you are learning a new topic of mathematics, the first thing that you should know is the language. What is the language? So that I'm defining the language of probability. So what is an experiment? So experiment is a broad term. So it is in any process or any activity. But what it does is it produces some outcomes. But all these outcomes somehow are uncertain to us. Okay, so there is an uncertainty in those outcomes. I'm giving pretty broad definition. I'm not pinpointing this. Rolling off a die can be considered an experiment. Why? Because there's a set of possible outcomes which we can know that this set might happen. Again, there is a sure shot that one of these things will happen, but which thing will happen, we don't know. There is an uncertainty about that. That's what experiment is. So in probability theory, an experiment is any process or any activity that produces a well-defined outcome. While the specific outcomes given in the experiments, they cannot be predicted with certainty, but we at least have the set of all possible outcomes with us. Okay, and we can analyze them. So this is an experiment. And then from this experiment, we have what is called as a sample space. So now you saw what experiment is. We can have a broader sense of experiment. Anything that probably you do can be somehow fit in an experiment if it has a set of outcomes, and those outcomes cannot be predicted with 100% certainty. There is some uncertainty associated with those outcomes. So now what the sample space is? Sample space in short is the set of all possible outcomes. Set of all possible outcomes for an experiment. Now we'll again respect the mathematics. So this experiment, we will not write it as experiment, we'll write it as E wherever we see it. So this sample space will be written like this S. We'll just use now shorthand notations. That's what mathematicians do. You have the huge English first, and after that you have this verbosity. To reduce the verbosity, you just introduce these symbols. So now if you see an experiment, let's suppose if an experiment consists of determination of sex in a child. Determination of sex in a child. If you see this in the experiment, so you know the outcomes. The outcome is boy or girl. So this is the outcome, possible outcomes. So and then we can say this is the sample space that we have. but you cannot say with certainty, okay, this will be the only outcome that is possible. So if it's the only outcome, then we have removed the part of uncertainty in that, then it won't qualify as an experiment. Similarly, if you see, let's suppose if you are interested in horses, so you have 7 horses and these horses are in a race, so you can see what is the position of different horses in that race. Let's suppose you have 1 2 3 4 5 6 7 horses, okay, and then you will see which horse came first, which horse came second, which horse came third, something like this. So this again is an experiment. So there are a lot of permutations possible, okay, there are a lot of if I say horses are A, B, C, D, E, F and G, so these are my 7 horses, okay, and they can occupy these 7 places, okay, based on their strength. Let's suppose how faster they are or how good they are fed, and depends how good trained they are, so they'll occupy one of these positions. So there will be a lot of permutations possible. Now all those possible permutations is our sample space, okay, so I'll say all the permutations. This is one permutation where let's suppose A, B, C, D, A got first place, B got second place, C got third place, and something like that. And let's suppose B, C, A, something like this. This can be also a permutation. So number of permutations, we have also seen that is 7 factorial over here in this case. So all the permutations in this case is our sample space. So similarly, if you let's suppose have coin, give me a second. So if you have a coin, if you flip the coin, okay, and in that you will have head or tail, but with certainty you cannot say whether it will land at head or it will land at tail. This again is an experiment, and this is the sample space. Similarly, if you can toss 2 coins, so there will be possible outcomes. Either it can be head, first coin landed head and second also landed head, or head or tail, or tail head or tail tail. So these are all possible outcomes that we have. So this is our sample space in there. Okay, now you know about these sample spaces. Now the thing is how to construct a sample space. That sometimes can be a question. So if you are given an experiment, you should model that thing and you should come up with the experiment. We should come up with the sample space. So now what this sample space, how should you construct the sample space? The first thing you should see is the individual events that you are putting, the individual elements that you are putting, they should be mutually exclusive. Mutually exclusive. So I am now writing what are the characteristics. So what are the characteristics? So when you are constructing a sample space, suppose you are given an experiment and you have to construct a sample space for that. So the first thing that when you are putting these elements, these elements, so what you should do is you should ensure that each outcome or individual outcome, so it should be mutually exclusive. That means the sample it should have distinct and independent. Okay, if in other words, no 2 outcomes should happen together. Okay, by this I mean no 2 outcomes happen together. This is the first characteristics of when you are constructing the sample space. The second thing is it should be collectively exhaustive. The second characteristic is it should be collectively exhaustive. Okay, right now what we are doing is we are putting the probability lingo in place, so that once we use these terms we know, and these things are there which we should respect while we are modeling the probability problem. The first characteristic of sample space, so these are characteristics of sample space. The first thing I said, whenever you are constructing the sample space, so you should ensure that they are mutually exclusive. That is, no 2 outcomes should happen simultaneously. They should be independent. If one thing happened, we should be sure that other thing has not happened. This is about the sample space. And the second thing we should also respect is collectively exhaustive. So what that means is the sample space that you have constructed, it should cover all the possible outcomes. Okay, it should cover all the possible outcomes. Okay, by that I mean this. So there should be no missing possibility. Basically, there should be no missing possibility. Let's suppose if you roll a die, you know there are 6 possibilities. It can land up 1, 2, 3, 4, 5 till 6. So if you just read in the sample space, if you said 1, 2, 3, 4 and 5, so you basically missed one outcome, one possibility, that is 6. You should not do that. That won't be considered as a complete sample space. So sample space should have all the possible outcomes in it. And the third thing that is there, it should be at a right granularity. So what is this? So basically when you are constructing sample space, you should be thinking how much granular do I want it. By that granularity I mean how much detail should it be. Let's suppose if you are flipping a coin, so in this what you can say is there is a possibility that it head might appear or tail might appear. So sometimes if you feel okay, flipping of this coin is somewhat related to weather, So now I am giving you additional information. Flipping of coin is related to weather. Is related to weather. If you have this information, I'm just giving a very basic example, but you can extrapolate it. So you have a coin. Let's suppose this coin is somehow connected to maybe skies and stuff like that. When you flip it, so based on this coin flip, the weather is determined also. So in this case, if you are asked, okay, construct a sample space for this, now you will have to choose a granularity. You will say, okay, the possibility is head and possibility is tail, but with this also now I have possibilities head and rain, okay, or head and sunny, something like this. Oops. Head and sunny, let's suppose, if there are these two conditions of weather, and tail and rain, and tail and sunny, something like this. So now you have to choose how much granular do you want your sample space to be. Okay, that depends on basically the experiment. Let's suppose if I gave an experiment where I give you a coin and I said the coin had some association with the weather, so then you will construct maybe sample space like this. And now if you see this is collectively exhaustive. The first thing is that, and then they are mutually exclusive. If it is head, it will rain. Okay, if it is it can be head or rain. It cannot be, let's suppose, head or rain and tail and rain. It cannot be like this. Two things cannot happen simultaneously. Only one of them will happen. So this is that collectively exhaustive. This is mutually exclusionist. Collectively exhaustive is I took all the possibilities. I did not left any outcome. So here I assume that the weather can be only rainy and sunny. This is just an assumption. This can be wrong. So then you have to choose right granularity. So you have to see how much detail should I put in the sample space. Sometimes you can remove the details. So let's suppose if you know that there is nothing that weather has to do with this flip of the coin, so you will remove this. You will say just there are two possibilities, head and tail. Now this is the right granularity because it makes sense in the world. But there will be a lot of experiments where you will have to consider the sample space. Now the sample space can be of different types also. If you see the first type can be finite. All the things that we have seen so far is finite. So you saw head comma tail, there are finite number of elements in this. Okay, but the second thing, it can be infinite. So in infinite, how it can be, let's suppose you have a dart board where you are throwing, let's suppose, the darts on that. You might have seen these shooting games also. So let's suppose this is the 1x1 board, so in which you will have to let's suppose you either throw a dot or maybe you'll have to fire a bullet onto this. So now you can see this, each point has some 2D coordinate. Each point has some coordinate. Suppose here, if you consider this is 0.5, say 0.5. So this is the coordinate. Now if you see, it has infinitely many of these points. Now the sample space lies in here, but you can see this point, these number of possibilities are infinite. Okay, and they are, in this case, they are uncountably infinite. And we'll also deal with this infinite separately, but here you can just remember there are two types of sample space that we can have. We can have finite set of outcomes, or we can have infinite set of outcomes depending on the experiment. Okay, and these are all the things that and this finite, even sometimes you can also have in the finite, you can have discrete. So discrete means, let's suppose you have this discretized outputs, or you can have this continuous. So oops, is it happening? So in this, what I'm saying is you can have with this finite and infinite, you can have the discrete sample spaces. So by discrete I mean each unit will have a certain value. So in this flipping of coin or rolling of a die, these are also finite, but sometimes things can be infinite and discrete. Okay, if only one thing happens. Discrete basically means it's in chunks. So if you see roll of a die, you have 1, 2, 3, 4, 5, 6. So this is discrete. It has discrete units in them. And again, you can have a continuous sample space where you can take continuous values. So this is discrete, and you can have continuous. So in continuous, you can have values 1.2, 1.223, 1.224. Let's suppose in this, I can give an example. If you have to see life of a bulb, life of a bulb or a lamp. Okay, or lamp. So there it can take these continuous values. Okay, the outcome is continuous. The sample space basically consists of these continuous values. The one thing is it can be finite or infinite, or it can be discrete or continuous. Discrete means it will take discrete values, but sometimes it can also take continuous values. Like in continuous, I said life of a bulb or a lamp, or height of a person, or temperature, or time, or weight of an object, or things like that. All these things will take continuous values. But if you see in this discrete, flipping of coin, you see head or tail, that is discrete. If you see rolling of a die, it will take discrete values. Okay, and number of students in the class, it can be anything, but it will be discrete. It won't be continuous. It will be discrete values. It can be infinite though. So discrete also can be infinite. So if you see number of students in the class, okay, you never know how many there can be 0 students, 1 student, 2, 3 till infinity, let's suppose, but that will be discrete number. It won't go into the continuous range. Okay, and again same thing, the number of cars passing through a toll booth. It will be again discrete number. It won't be 1.2 cars passed. It will be 1 car, 2 car, 3 car, something like this. The values will be integral values. Okay, non-negative. If I say not just non-negative, we can also put negative values in here, but that's why it has been used. Discrete values will be there. So finite, infinite, discrete, or continuous. Okay, and they're pretty much different though. This is about sample spaces. So in summary, what I'll say is, so in sample spaces, you will have to follow certain characteristics. As I said, they should be mutually exclusive, they should be collectively exhaustive, and they should be at the right granularity. Okay, and then you saw the types of these sample spaces also. So we have an experiment, and then we have a sample space. So now a subset of a sample space will be called as an event. Okay, you will have an event. So any subset of the sample space S, that will be called as an event. So let's suppose you have this two coins which you flipped. So this is the possible. So head head, head tail, tail head, or tail tail. So this was the sample space that we had. Now what I said is, if you let's consider, if you say tell me the outcomes in which the head came first. So you can say head, tail, head, head, something like this. Okay, for other two, the tail came. So this will be an event. So this will be an event. So this event is basically where in the first flip of the coin, the head appeared. So that means this is a subset. As you can see, this is a subset of this. So a subset of the sample space is considered as an event. Okay, and now events, it is not necessary that event will be disjoint. Some events can assume, let's suppose if I again define one more event. So this is event 2. The event 2 is number of heads. Say at least one head. Let's suppose at least one head. So head tail at least one head, tail head at least one head, head head at least one head. So now you can see in event 1 and event 2 there is some overlap. What is the overlap? So overlap is this head, this head, at least one head. This is head. So this is overlap, and here you can see this is the overlap. So here these two elements are also in here. So you can now see that in the events that can be overlap. So in nutshell, I would say that event is basically any subset of the sample space. So in terms of, let's suppose, and all these now and profound idea here is, because now we had set theory, otherwise it would have been astrology. So let's suppose we would have quantified the things and would have done this and I would have said everything in the words. Now because we had a framework, we had developed methodology of sets which we call set theory, based on which we use these symbols in every concept of set theory here. That is why this probability became the science that we wanted it to become, because we had a notion to represent these things by using the set theory. That's why we, in the prerequisites, we covered the probability part first, because we had a notion now and you used that notion into this. So you said, okay, I'm using head. If you can see this, so the sample space basically is a set. So if you see in that way, now you see this event is a subset. Okay, now we are again using the lingo of the set theory. So if you see these two events, if I'm saying they're not mutually exclusive, that basically means there is some intersection between these sets. If there is no intersection, so if the intersection is phi empty set, there is nothing intersecting, I'll call them these are disjoint sets. They have nothing in common. Okay, I'll call them these as mutually exclusive. They're happening independently. So all the set theory can be used. That's why we covered the set theory, and all these concepts will be again used. So now we'll have to somehow define the probability. If you now know what an experiment is, what the sample space, and what's an event, I don't think much discussion is needed on that. Any questions on this? Any questions on these terminologies? Now we'll have to define probability. Once we have the notion what an experiment is, what a sample space is, and what an event is, so we'd like to define probability. Okay, so how to define this probability now? Define probability. Now the thing is, there are different philosophical debates what probability is. Okay, how probability should be seen, because I said different schools of thought are there. But somehow if you could come to the definition, and whatever school of thought you are from, but you could abide to those definitions. You could say, okay, you could not a definition, you could abide to those maybe axioms or whatever you have. So after that you have your debates what probability is, whatever they are, you have different takes, different perspectives, but at least certain rules, you are following certain rules. And I don't have a problem with the point of view that you have or the definition that you might put. Your philosophy might be something, but at least what are the axioms or things that we'll put, it should respect those things. Okay, so the first naive approach to define probability that you have seen in your primary, secondary grade level. So we defined this by using the frequent test ever, or which called as relative frequency definition, in which we said probability of an event. This is how we'll write it. So this P of E will represent the probability of an event. probability of an event. We'll write it like this. So we'll say, let's suppose we have S as our sample space. So S is our sample space. Okay, and then let's suppose some event E is there. So this is our sample space. So obviously this E will be a subset of this S. Now probability of E is equal to number of the favorable events. Number of favorable events divided by the total events, or the sample space, howsoever you quantify this. So how many favorable events are there? How many, or I should say favorable outcomes rather. Outcomes, not events. Okay, how many favorable outcomes are there in my event, and how many total outcomes are there? Okay, and then you have to perform this basically experiment n number of times. You have to keep on doing this. Okay, these are the total number of possibilities, and it's sometimes a natural idea. Let's suppose in head or tail, you will say, okay, my head is this number of times, I found head these number of times, and total number of trials were these many. So this sometimes feels like a natural idea. So this is, I'll write it naive definition. Naive definition of probability. But there are assumptions, very strong assumptions that it makes. So there are a lot of assumptions which this definition makes. So what are the assumptions that that the definition makes? The first assumption is that all of these events, these outcomes are equally likely. Outcomes are equally likely. Equally likely. What is the meaning of that? By that I mean that all the outcomes that you have at the granular level, so they have equal probability of happening. Let's suppose in head comma tail, you are saying that this is quite obvious to say if coin is fair, so this is having 0.5 probability. So here we had two possible outcomes, so each outcome had the same probability. So in the, let's suppose in the die 1, 2, 3, 4, 5, 6, so here intuition says that if this die is fair, but the question is how we define fair die. There can be a circular definition also, so you should not get into circular definition. A fair die is, but the probability is 0.5. So I'll say, okay, why is it 0.5? Because it's a fair die. Okay, there will be a circularity. So but here, if this die seems to be, the edges are quite good and it is almost symmetrical everywhere, so you'll say that each of these outcomes has 1/6 probability. So that's what I mean by equally likely. So each of the outcome is equally likely. So this definition assumes this. So this is a very I'll say drastic assumption, or this is a very wild assumption, because everywhere you will not see this, that outcomes are equally likely. So in this definition, in this naive definition, when you have this number of favorable outcomes divided total outcomes, so this assumes that all the outcomes are equally likely. So you should be very careful once you're, and second assumption that you're assuming here is that these experiments are done in the same conditions. Okay, the experiment, if the experiment is repeated multiple times, so it is done in the same conditions, which is again quite improbable. Okay, the conditions won't remain same. Let's suppose if you flip a coin, so heredity will get changed, something will happen. So you cannot ensure that this again one more assumption, that you are performing the experiments under the same conditions. Like if you are having 1,000 trials, all 1,000 trials were done in the same. What is the trial? So trial is basically one experiment. Doing of one experiment is called a trial. Okay, and why is this what is this probability used for? I should actually tell you this probability. We are going to also cover statistics. So this probability, if you see, the probability basically will tell you what will happen in future. So it will model a probability distribution, and based on that it will tell you what will happen in future. Okay, I should have also covered this in the definition part also. So that's what we are trying to do here. Okay, now if I toss the coin, okay, you saw the probability distribution, you are thinking, oh, okay, this coin is fair. So based on this, what I can say is I have modeled a probability distribution. Based on that, I can say what might happen in the future. So this thing talks about, probability talks about future. It says I have modeled the probability distribution, and based on my modeling, I think that this will happen in the future, or this is highly likely, or this is the probability of this event happening in future. But on the counterpart, you have statistics. So in that you have data. From the data you come with probability distributions. So that's where machine learning comes into picture. You have data. From the data you try to learn the distribution. So this is basically from data you come up with the distributions. Okay, from the distribution you go to the future. They basically are I should say same side, two sides of the same coin. So one is probability, where you have a distribution and you say something about future, and on the counterpart you have this statistics, where you have data, and from the data you model a distribution. You try to come up with methods to model distribution, and from that distribution you say what will happen in future, that will fall into probability. So I was telling you about this naive definition, where it considers that you have number of favorable outcomes divided by the total outcomes. So I said assumption, the first assumption is that all these outcomes are equally likely, and the second assumption is that these trials or these experiments were done in the similar conditions. Okay, I again said this again is a wild assumption, because most of the times the condition will not remain same when you have this. And there is one more problem. It also sort of restricts you that these total outcomes is finite. Total outcomes is finite. So what will happen if this will become infinite? So obviously this will go haywire. So anything there by infinity, it will come to zero. Okay, you'll say the probability is zero. So you assume it in order to apply this definition, the first thing that you should do is that you should ensure that these outcomes are equally likely. And second thing, it's a finite. These total number of outcomes are finite. So in IIC, what happened in one of my assignments, I used this definition. I was solving a probability assignment and I used the definition. You know, my half marks was deducted. And that question was probably of some 3 marks or something. The TA deducted half marks. You know what was the mistake? The mistake said you did not write that all these outcomes are equally likely, so I am using this definition of probability. So please be careful. Whenever you are using this, ensure that the thing that you are doing assumption is valid. Okay, so whenever you are using the definition, you should be sure that the experiment, the outcome that you have, they're all equally likely. So then only you can use the definition. And then also for the same conditions. And then I also said this total outcomes are finite. They should be finite. If it is infinite, so you cannot use the definition. But in most cases, you should first look for this or all the outcomes equally likely. Otherwise, you should not use the definition. Okay, this is quite naive definition. Okay, and there are a lot of problems with definition. I'll just maybe strike a conversation with you people regarding the problems it might have. Let's suppose if I ask you a question, what is the probability that there is life on Mars? Okay, what is the probability that there is life on Mars? Okay, any guesses? So if you see this, if you somehow construct the sample space like this, either there is life or there is not life. So it means there is 0.5 probability, because this is the possible outcome. Let's suppose the outcomes, if you see, I'll say okay, outcomes is life or there is not life. Okay, if this is the sample space, so I'll say both of them, if they are equally likely, then this is 0.5. So this also seems like quite wrong. Okay, this directly looks like wrong. It should not be 0.5. So if you see this as I said is quite an outrageous claim again. Why? Because I'm saying there is life is 0.5, there is not life, again it's 0.5. So but this is not the case. So even if I say, let's suppose, what is the probability that there is an intelligent life on Mars? So again, there can be or there cannot be. Okay, if there are two possibilities, if I say equally likely, then 0.5. And obviously both of these things are in contradiction. So there is life should always have higher probability than there is intelligent life. So if you see such experiments, then you cannot use such an approach. That's why there are a lot of these problems in this naive definition of probability. So then what is the thing that we should resort to? Okay, then there were a lot of people who thought, okay, there should be some alternative definition where we can come up with, and any perspective that you now have should, as I said, should somehow follow these definitions. Now they went to what's called as axiomatic approach. They said, okay, we'll come up with certain axioms. So now if you follow these axioms, we don't care if you use this definition or the other definition that you come up with, they should abide these definitions. Somehow you should follow these axioms, then your definition is done. We don't want to know your perspective. Okay, this is how you look at probability. But if your school of thought is somehow following these axioms, then we'll consider you that somehow you can use the framework of the probability. So this axiomatic approach, usually actually Kolmogorov came up with this. Kolmogorov. Okay, and why was this necessary? Actually, this probability is it is so counterintuitive, because if you go, let's suppose 350 years back, so you will see even Newton had wrong intuitions. Gamblers were asking Newton questions. They're asking, okay, what should happen? And Newton gave an answer because there was not this framework available. So he gave an intuitive answer, and that was quite wrong. Even the same thing, and there are these. The history of probability goes like it dates way back. So there are you'll see Pascal and these people, they were writing letters to each other, solving these probability questions. That's how these fields really emerged. That's in the initial go I said this probability is quite counterintuitive. So that's why you have to resort to this framework. Sometimes something might look like this, but it actually might not be that way. So you'll have to reason again. You'll have to see it from different perspectives. Okay, so that's why then people came with the axiomatic approach. You should come up with a certain axioms, and I told you that Kolmogorov was the person who came up with these axioms. So this was to address the limitation of this relative frequency definition, or which I just said as a naive definition. So that we adopted this axiomatic approach. Now you see this, we have the sample space. We have the sample space. Now you have to assign probability to it. You have to assign probability to the outcomes of the sample space. Now you should follow these certain axioms, and based on these are only, people sometimes say there are 2 axioms or 3 axioms, doesn't matter. So I'll tell you like what people sometimes do in the first axiom is embedded in the definition itself. But somehow if your definition abides these axioms, then we are okay. The first axiom says, let's suppose you have the sample space which is called S. Okay, now you have to assign probability to the outcomes of this. So if this is that, we should now have a function. Let's suppose we should have this function P, which will go from these events. So these events will be a subset of the sample space. Okay, we'll have this function P, which will take an event and it should map it to a number between 0 and 1. So this is the function. Okay, now we have this P is a function, probability function, which will take any event from the sample space and it will assign it some probability. Okay, or the outcomes, or it can take individual outcome, it can take a set of outcomes, and then that we call an event. So this event should be taken by this probability function P, and it should assign it a number between 0 to 1. Okay, now this function should have certain characteristics. Okay, this function is the first characteristic or the first axiom of probability. Okay, and sometimes this is called as, let's suppose, 0th axiom. Or maybe this is called as first axiom. That is, the probability should be between 0 and 1. So that's what I said. There's a function P which should take an event as input, and it should, as an output, it should spit out a number between 0 and 1. Okay, included. These are included. 0 and 1 should be included. The first axiom is that this P of S should be equal to 1. That means if you take whole sample space, okay, the probability of that is 1. That is, the sample space basically should happen. That's what I said in the definition of sample space. It should be collectively exhaustive. Okay, that is the meaning of this thing. Okay, P of S is equal to 1 basically means you should not leave any outcome. Okay, probability of S is this, or probability of event that is not there should be 0. Okay, a null event, nothing, basically probability of happening nothing should be 0. The probability of, actually the axiom says this is the axiom, and this is the inference that we can take from it. Okay, probability of whole sample space should be equal to 1. And then the axiom second says, this is called as additive axiom, axiom second. It says that if you have, let's suppose, 2 mutually exclusive events, you have an event E1 and you have event E2. So intersection between these events is nothing. Okay, there is phi, there is no intersection between them. They are sort of mutually exclusive events. So what you can do is the probability of these events, let's call this E1, I'll write it like this, probability of E1 union E2. This should be equal to probability of E1 plus probability of E2. Okay, probability of E2. So if there are 2 events, so you should basically, this is called as additive property. You should be able to add additive axiom. You should be able to add these things. So if you have 2 events which are totally mutually exclusive, they don't have anything in common. So if I am saying, okay, what is the probability of these 2 happening together? Okay, what is the probability of E1 union E2? So you should say that probability, you can just take E1's probability and E2's probability, you should add them. But given this, that they are mutually exclusive. So this is given that they are mutually exclusive. So by mutually exclusive, I mean this. Okay, E1 intersection E2 should be phi. So okay, this can be generalized to infinite union. So you can say probability of union of I goes from 1 to, let's suppose, n u of I. So if there are I events which are mutually exclusive, so their probability should add up. E1 plus, I should write in summation, I goes from 1 to n, probability of ei. Okay, so these are the axioms. So you can consider 3 axioms or 2 axioms. So what I said is, so in formal sense, when you have performed an experiment associated with the sample space, now there is a function associated with it which is called as P. So P takes any event as an input and it gives output as a number that is between 0 to 1. Okay, so this P of any event should lie between 0 to 1. Okay, so this is the first axiom. Sometimes people call it, let's suppose, call 0th axiom. Now this function should follow these rules. The first axiom it should follow is that probability of sample space is equal to 1. Probability of sample space should be equal to 1. And the second thing is, if there are events which are mutually exclusive, that there is no event which is sort of overlapping, there is nothing overlap in those events, so then it should follow this additivity. You should be able to add these probabilities. Okay, and now in order to define anything, so if your probability definition abides this, if your probability definition follows these axioms and it respects these things, no matter what perspective you come from, no matter what school of thought you come from, so if it is following these axioms, then we are good to go, because we'll reach the same conclusions no matter what we're using, no matter what's the perspective. So if somehow it is abiding these things, so we should be able to reach the same conclusion. Okay, so axiom 1 or axiom 0, which I said, it ensures that probability is always non-negative. Okay, it's non-negative. And the axiom 2 ensures that the probability of the entire sample space is 1. That is, you are not leaving anything behind, you are not leaving any possibility. And axiom 3 allows you to calculate probability of complex events, because you break an event into disjoint events, into these disjoint sets, into mutually exclusive events, and then you just add them up. Okay, so as a consequence of this, as I said, the probability of an empty set should be equal to 0. Okay, and I just gave you this finite additivity, so this also goes to this can also go to infinite additivity. Now we'll see some propositions based on that. The first proposition we'll see is that probability of an event complement is equal to 1 minus probability of event. So if you have a probability of an event which is P of E, okay, so if you have this 1 minus probability of, you should be having the probability of complement. That's what I said. I think in one of the problems, maybe it was a birthday problem, I suppose, birthday problem, a subproblem, where I said this should follow from the axioms of probability. So this is proposition 1. Proposition 1. That is, if you have an event, its probability is P of E. If you say 1 minus probability of E, then you should have the probability of its complement, and you know what complement of event means. So this is from the set theory. So whatever outcomes are in the E, so E complement basically means those outcomes should not be all the outcomes that are there in the universal set, and they should not be in the E. So this is event complement. So now in order to prove this, what can we do? We now, from the first axiom, we know that probability of S is equal to 1. Okay, probability of the whole sample space is 1. Now you know that if you have E and you have E complement, if you take union of those things, okay, so you know that this comes out to be the sample space. If you have the event and you take the complement of the event, that means it's a sample, it's your sample space. So what I can say is, I can say probability of E union E complement is equal to 1. Okay, this is probability of sample space, so this is probability of E union E, because this is equal to S. Now what you can do is, because of the axiom 3rd or axiom 2nd, additivity axiom, so you can say probability of E plus probability of E complement is equal to 1. So why would I apply it here? Because E and E complement are disjoint. So E complement intersection E is equal to 5. So these events are mutually exclusive events. Okay. So what I can now write is probability of E complement is equal to 1 minus probability of E. Okay, this is a conclusion or a proposition from the axioms that we have, that if you have an event E, so the probability of its complement of that event is 1 minus probability of E. So this will be very useful in a lot of problems. So when we are going to solve even birthday problem, so in that birthday problem, you will probably solve the complement of the problem. So if you use a combinatorial approach, so I think we have done that in one of the class. So this is the result that we use there. Any questions still here? Any questions? So now this is the first proposition, and then there is second proposition that I would like to discuss with you is this. So if, let's suppose, you have an event E and you have an event F, and if this event E is subset, or it is contained in F, so it is something like this. This F is there, or this E is contained in this. So if you have an, I'll make a lot of Venn diagrams now. So this is your universal set. Let's consider this as universal set. Okay, and then you have this F as an event. Okay, I should write it like this. So this F is an event. Okay, then you have an event E. So now you can see E is contained in F. So it's read as E is a subset of F. So now what the proposition says is that proposition second, it says that the probability of F should always be greater, or I should say probability of E is less than equal to probability of F. So if one event or one of this is contained in F, so this is logically, it is quite intuitive to see it. So now you might resort to prove it mathematically, so that's quite easy, but you can see it from here. So if this has some probability, so obviously this has less probability than this event happening. Why? Because E is contained in F, or E is a subset of F. How to prove these things? There's a quite visual proof that you can clearly see over here, but if you want to prove it mathematically, so what to do? So you can write this F as like this. F is equal to, you can say this can be broken down into E union, because now E is a subset. Okay, you can break it down into E, take the E and take what is outside this, take this E, whole of the E, and take this ring. Okay, take this much. That is F basically. So I am breaking down this F event as E plus whatever is not in there, in E. So that is E union. So what is not in there in E? So whatever is in the F. Okay, you have to take this F and then you take E complement, intersection E complement. Whatever this basically says, take f, the whole f is this much, okay, and the intersection with e complement was whole of this, or e complement was whole of this, okay, including this ring. Now I said what is the intersection of e complement with this e, so that means this ring only, okay. So I wrote f like this, so I said e and whatever was outside, whatever was this ring basically. So this is this, I'll write it ring and e, so I can rewrite this f like this, okay. Now what I can do is I can say probability of f. Now both of these things, if you can see, they are mutually exclusive because e and this have nothing in common. So I can write probability of f is equal to probability of e union probability of f intersection e complement. Now you can see this, I should add plus. So if you see this term, so as you know from the axiom 0, probability should always be equal to greater or equal to 0. That means p of f should be greater or equal to p of e, because you are adding some term to it, you are adding something, and which is a non-negative number. That means this is less than equal to, if it is 0 at worst, so this will be equal, so that's what this equality is for. And if it is greater than 0, then this will be a strict inequality, this will be a strict inequality over here. So you can check this. So this is what I said the proposed second. This is called as monotonicity. So if one, you have a subset and there is a superset, there is f which contains this e, or e is contained in f, then the probability of e should be less than equal to probability of f. So this again is from the basic axiom. So here I used axiom 0, and here if you see, in order to break this, in order to break these two things, I used axiom of additivity, which I called as axiom second, or additivity, okay. Then we have also in this combinatorics, we also came to this inclusion exclusion principle. So that also can be derived from this. So I can also write proposition third, which we discussed in combinatorics, inclusion exclusion. If you have now an overlap, so what should you do? So you have this p e union f. So if e intersection f is not equal to phi, so if there is some overlap, so now you know that this should be equal to probability of e plus probability of f minus probability of e intersection f. So now this also can be derived from axioms of probability, axioms of probability. So here I leave you this as a homework. You think how I can derive it using the axioms, and in the next class, so we probably will discuss this first and then we'll go to the subsequent things, and after that we'll have a good treatment of the probability. I was actually going to discuss the example with you based on these axioms, but maybe we'll discuss the examples in the next session. If you have any questions, please ask it right now. I'm stopping the recording. In the last lecture, we started with the first naive definition of probability. If you see, we said that naive definition has a lot of assumptions. The first assumption was that each of these outcomes should be equally likely. So we're constructing a sample space from that. We said if all the outcomes that we have there are equally likely, then we can use a naive definition. The naive definition was if you have to calculate a probability of an event that was equal to number of favorable events, or number of favorable outcomes rather, number of favorable outcomes divided by total number of outcomes. This was the naive definition. So it had a lot of assumptions and the problems with it also. And then we made a transition to what we named as axiomatic approach to probability. So in this we said that there are three axioms, or you can say two axioms, and in which we basically define some of these axioms, and we say based on these, if you somehow now define the probability, it should abide these rules, or it should follow these rules. So among them, the first thing was probability is between probability of any event is between 0 and 1. Okay, so basically this probability is a function. So I defined it that way, that if you, let's suppose, have now a sample space, so sample space will consist of outcomes. So now you have a probability function p. So it takes input as an event and then it assigns it a probability that is between 0 and 1. So it takes input as an event e and gives it the probability between 0 and 1. So we consider this as axiom 0, or we can call it axiom 1. That means probability is between 0 and 1. So 0 means that it's almost impossible. Why did I say almost? Because sometimes if we say probability 0, it doesn't mean it won't happen. So it will say, like, let's suppose almost impossible. So I'll put a star in here, and this is sure this will happen. And the second thing that we said about probability was, so probability of the whole sample space was equal to 1, or which implied that probability of empty event is equal to 0. Okay. Then the other thing we said is, if we have the events which are disjoint, that is these events do not have anything in common, so we say probability of the union of, let's suppose, E of I. So if all of these events E of I, they don't have anything in common. Okay, so probability E of 1 to n, it can be also written as summation of probabilities of individual events. Okay, so I think these are the three axioms that we discussed. And then we also discussed about the propositions that are that are the result of these axioms, and we said a lot of things. I think the last axiom we discussed was the inclusion exclusion. Inclusion exclusion. In which we said, if now let's suppose there is some intersection between these events are not disjoint, they are not mutually exclusive. So what is the meaning of mutually exclusive? That if one thing happens, if other thing does not happen, then we call them these events are mutually exclusive, that they cannot occur together. And if some events are like this, so we can't tell them that they are mutually exclusive events, so we call them E1 and E2. So now E1 intersection E2 is not equal to phi, so they have some intersection. So this is that intersection part, if you see. So what does the include exclude principle say that? So if you have to now compute the probability of E1 union E2, so we said you can say probability of E1 plus probability of E2 plus minus probability of E1 intersection E2. So I told you to do it as an exercise and prove it from the axioms. I hope that you have done it. So now this can be generalized also. This thing can be generalized. So if you have probability of E1 union E2 union E3 till En, so this thing can be generalized. So probability of E1 plus probability, let's say probability of EI, probability of EI. So summation I goes from 1 to n, let's suppose. So this will be the probability of whole of these things. Then you will have to subtract probability of E I E J. So I'll write E intersection E J, I'll write it as E I E J, something like this. Okay. So if you see this, again you will have to sum this up. So I less than J. Okay, and this goes from 1 to again n. So 1, 2, 2, 3, something like that. Okay, until you go to the n. You'll have to let's suppose subtract these things, and then you'll have to add. So you'll have to add triplets. You'll have to then subtract and keep on doing this. Okay, so you'll have to keep on doing this. At the end, you will have 1 minus 1 raised to power n plus 1. So either depending on how many terms you have, let's suppose in this we had 1 and 2 terms. So E1 and E2. So now this was minus 1, 1 to the power n was 2 plus 1. That's why we got a negative sign here. So in order to adjust for this, but the last term should be added or subtracted. So you add this minus 1 n plus 1, and then you write the last term, probability of even all of these events till n. Okay, so this is the generalized inclusion exclusion principle. If you see this, pretty much easy to prove. Okay, so make a box around it. Okay, so I hope this is also visible. So I'll write it like this: P probability of E1 till En. Okay, so this is the generalized inclusion exclusion. Okay, you can also prove this. Now let's start by seeing how we can utilize this. Now you have got at least the lingo of probability. You have understood the language of the probability, and you also know what is the meaning of an experiment sample space. So in order to see how do we use the probability in our day-to-day life, so we'll now start with initially some basic questions, and we'll also go with the naive definition first without going to the action approach. So we'll start with some questions so that you get a notion at least how to use it when you face some real world situation, or you face a question, or maybe some situation in machine learning, in deep learning, or maybe in real world also. Okay, so let's start with the basic problems and slowly we'll level up. And I would have connected this including experiment principle with a problem, but that's a bit advanced problem, so that's why I'll just put this on hold. So we'll do a problem on this, but before going to that problem, I would like to go with the basic problems. Okay, let's suppose we have 3 coins. Now the question is coming. So you have 3 coins. The coins are, we have 2 5 rupees coins. You have 2 5 rupees coin and a 1 10 rupee coin. You have 3 coins. I won't write all the details in English, so I'll just spit it out so that you can focus on here, and then I'll give you some time to understand and maybe come to an answer for these questions. Now we have 3 coins. So 3 coins of different denominations. 2 coins are of 5 rupees and 1 coin is of 10 rupees. And all of these coins are tossed. Okay, so all of these 3 are tossed. So what you do basically is, so whichever coin lands at head, you win that amount. So whichever coin lands at head, let's suppose you have these 3 coins, 5 rupees, 5 rupees and 10 rupees. So if let's suppose head appeared on the 10 rupees coin, so you will win 10 rupees. If head appeared on no coin, so you will win nothing. So but in order to enter this game, you are giving 10 rupees. So this is the entry fees. Okay, so now the goal is to determine the probability of winning some money. At least you should win some money. You'll have to compute the probability of that. The goal of this problem is to determine the probability of winning some money. Determine probability of winning some money. Keep in mind that entry fees is 10 rupees. Entry fees is 10 rupees. Okay, and then what you can win is based on these coins. So whichever turns ahead, and you have 5 rupees and 10 rupees coin. So whichever has head once tossed, after we toss, and if it lands on head, so you win that much amount. Now the question is to determine the probability of winning some money. So if you see the first thing I said, whenever an experiment is performed, you should construct sample space. Okay, now you have to construct sample space for this. Sample space basically means what are the all possible outcomes. So there are multiple ways you can construct sample spaces. So if you remember the lecture on sample space, there I said sample space is basically all the outcomes. It depends on you. It should be granular, like right granularity. You determine what sort of granularity you want. Let's suppose if I want to construct sample space, the first approach is list all the possible win outcomes. Okay, I can win 0 outcome. Basically, I can win nothing. Okay, but I can win 5 rupees. How can I win 5 rupees? So let's suppose if this turned to be head and this turned to be head, because I have entered in the tournament by giving 10 rupees, so I can earn 5 rupees. Okay, this is just earning. I'm saying when I win something, so winning price. So it can be 0. So 0 basically means you just had one head over here and you lost all the money. You lost basically 10 rupees, and that's basically 0 winning. Then you can have 5 rupees winning. You can again have 10 rupees winning. You can have 15 or you can have 20. So this is the winning possibility. Okay, this is the total possible outcomes of winning. You can either win 0, you can either win 5, you can win 10, 15 or 20. Okay, how? And you just have to, let's suppose if you want to win 15. So how can you win 15? What you will do is you will win all of these. So you will say this is head, this is head, this is 15. So now if you consider that you have paid, let's suppose 10 rupees for that. You have paid 10 rupees. So then we can, let's suppose, remove these 3 outcomes from this, because this is the overall winning. And if you have to say total winning, okay, total winning, if I reduce my amount, then you can subtract these things. So now the total possible outcomes, if I remove my 10 rupees, I'm just seeing that what is the win possibility without, let's keep my 10 rupees for the side now. So these are the win possibility. I can either win 0, 5 rupees, 10, 15, 20. Okay, and here I'm considering that 10 rupees fees I'll subtract maybe later. These are the winning possibilities if I say head. And now if you see this 20 rupees, this 15 rupees, these are the only things which will give me overall winnings. Okay, the rest will just neutralize. Either I'll be in loss and I'll be in gain. So this is one type of sample space. So this is listing all the possible amounts you could win. Okay, so this is you could win, but here I'm not assuming that this 10. If you have to compute overall winning, then you will subtract this 10. So how can you land at this 10? Basically, let's suppose this can be head and head, and then tail, head and tail. Okay, so you will win, let's suppose, 10 rupees, or this can be like this, head, tail, something like this. Okay, so you landed this. This is one sample space. We have constructed sample space by listing out all the possible winnings. And the second sample space can be consider the net gain or loss. Let's now compute at the sample space. In the first sample space, we said, okay, let me just list all the possible winnings without considering the entry fees. Now if I consider the entry fees, okay, then I can list total loss or gain. Okay, this is loss or gain. So this was total net winning So this was total winnings. Now I'll say net loss or gain. So something like this. So what can I lose? We'll start from losing. So I can start from losing minus 10. So everything will be lost. Why? Because if all of these turn into tail, then I'll lose my 10 rupees. Okay, or I can lose 5 rupees. How I can lose 5 rupees? So let's suppose this turned out to be head and rest turned out to be tail. I have given 10 of the entry fees and I just have now my 5 rupees with me because I lost 5 rupees. So you'll have minus 10, minus 5, or you can have 0. If let's suppose this turned out to be tail and these two head, because you have paid 10 rupees. Now two things turned out to be head. You won the 2 5 rupees coins, but you already had paid 10 rupees for that. So that means net you had 0 profit. And after that you can also win 5 rupees and you can have 10 rupees. That's what I said. These two will give you the winnings because 10 entry fees and here 10 entry fees. So here you have possibility of winning 5 rupees. Here you have possibility of 10 rupees. So this is another sample space. So now I am teaching you how to basically construct sample space. The first thing that you should determine. So if you have to compute a probability of something, so you should see what are the all possible outcomes, and then you will probably see, let me assign probability to these individual outcomes, and then I'll see what are the favorable outcomes to me. Okay, and then if all of these things are equally likely, you can use the naive definition of probability. If not, then maybe you can do something, but at least the first thing is to construct a sample space. This is one way. So what you did is you said winning this, net losses, and the way of constructing sample space is let me have lose, win or draw. Okay, that basically means, so if you lose, these two possibilities are there. Okay, so winning, these two possibilities are there, and then draw basically means neither one not lost. So this is another way of creating a sample space. Okay, so these are possible outcomes rather. So these are possible outcomes. So now you have to assign probability to all of these. Okay, so who are you following this? So now the point is, I have listed all the possibilities. I have listed different possible outcomes. So now I should assign probabilities to these outcomes. So let's suppose if all of these are mutually exclusive. Let's suppose all of these are mutually exclusive. So what I can do is, if I assign probability to this, if I assign probability to this, I can say if probability of winning this is 0.1, probability of this is 0.2. So I can add them together if they are mutually exclusive. If they are not mutually exclusive, then I'll use inclusion exclusion principle because that's what we have learned. Now my task is somehow to assign probability to these outcomes. Now how to do that? Okay, how to assign probability to the events? Okay, let's see again. Let's construct sample space in this fashion. So now you are tossing 3 coins. You are tossing 3 coins. This is what you are doing. So now what we can do is, it can either be like this. So you can have, let's suppose, one head. The first coin you can mark them as 1, 2 and 3. 1, 2 and third coin, something like this. So this is 5 rupees and 10 rupees coin. So you can say first this is head, second let's suppose is also head, third is tail. So now I can write all the possible outcomes, head, tail, head and something like this. Okay, so what I'll do is I'll write head and head. So this is head for the 5 rupees, head for 5 rupees, head for 10 rupees. Then I can write head and tail. Okay, then I can write let's say, so it is better for me to write in 0 and 1s. So I'll write now head and tail for you people. So this is 3 heads and 3 this. So head, tail and head. So this is head, tail and tail. And this is let's suppose tail, head and head. This is tail, head and tail. This is tail, tail, head, tail and tail. So how many possibilities? 1, 2, 3. I think these are 8 possibilities. So it's 8 cover them 1, 2, 3, 4, 5, 6, 7, and 8. Yes, these are all the possibilities that we have. So this corresponds to the first 5 rupees coin. This corresponds to second 5 rupees coin, and this corresponds to 10 rupees coin. Okay, these are again all the possibilities. So how they land? Either we can have 3 heads, and now you have an assumption, because if we consider now all the coins are fair, so each of this is equally likely. So each of this is equally likely. So each of these has 1 by 8 probability. So each of these things have 1 by 8 probability. Now based on this additional information, I can assign value to these. Okay, so let's suppose if I consider this, so how much will I win in this situation? In this situation, how much will I win? So now I'll write win or lose. Okay, so now if you see, this is head. So if you just have to construct give it this, so you're just saying what probability should be assigned based on this. Or maybe we can just assign probability to win or lose. So this is 2 heads, you are winning 5 rupees, and then you are losing 10 rupees. So here net basically is, so this is head, head and head. So you are winning 5 rupees, 5 rupees, you are winning 20 rupees, but you have paid 10 rupees. Okay, so here net total is 10 rupees. So here you are winning. So in this possibility you are winning. Okay, so in here, so you win 5 rupees, 5 rupees, but you lose 10 rupees. So overall you win 0. Okay, and after that, here you have had the 5 rupees and 15 rupees. Basically you win overall 5 rupees over here. Here, so 5 rupees, lost 15 rupees. Okay, and net 10 rupees, so you lost here. So here you lost a lot. So if you see, so you lost initially, you just won the 5 rupees over here. You have won the 5 rupees and you lost these things. So net you lost 5 rupees minus 5. Okay, do correct me if I am doing some calculations wrong, and do help me over here. So is everybody understanding this thing? The thing basically I am doing is I basically have a outcome, possible outcomes, and now I am seeing, okay, these are all the possibilities that can happen. Now there it is. Here I can make a legal assumption. So it looks good to make the assumption that I can say all of these things have probability 1 by 8. Now if you see, I only win in these 3 situations. Here I win 10 rupees, here I win 0, here I win 5. At least I am winning. Let's suppose in these 2 cases I am winning. So the winning probability is 2 by 8. Okay, so winning probability is 2 by 8. And because here I am winning only in these 2 scenarios. And why are these possible? So they are possible over here. Okay, so this is giving me basically 10 rupees. So this is this case. And in this case, if you see, so this is this case where I am winning 15 rupees. Okay, so in these 2 scenarios, there is a possibility of winning an amount. Okay, so I am giving this as 1 by 8, 1 by 8. So this is 2 by 8. I think we have a question. Yes, question. Now, based on this information, based on whatever information I had, I can assign the probability to these sample spaces. So consider now this probability. I'll take an event and I'll have to assign them probability between 0, 1. And then if they are mutually exclusive, I'll use directly additive principle. If it's not, then I'll have to use mutually exclusive inclusion exclusion principle. So what you can do is, if let's suppose I have to assign the probability to this win, lose and draw, something like this. Okay, now usually what people do is, this is a mistake that we already did in previous, and I told you that's about the probability that there is life on Mars. So we said if we consider sample space like this, there is life or there is not life. There are only 2 possibilities. So can I say this 1 by 2? No. Why can't I say that? Because there is life and there is not life. The first thing is not very granular, and second thing is, how can I conclude that these both are equal? Both of these events are equally likely. Okay. Similarly over here, if I directly say there are 3 possible outcomes, it can be lose, win or draw. So I can assign probability 1 by 3. I can give probability to 1 by 3, 1 by 3, 1 by 3. But no. Why? Because lose, win and draw. Who is telling you that there is these all of these are equally likely? So in order to solve that, you are making it more granular. You are saying, okay, what are the possible, and then based on that you will see it. So here in this situation, I said you will win 10 rupees. Here you will win overall win loss. So here you will win 0. Here you will have 5 rupees, and here you will lose 5 rupees. So in this case also, head you will 15. Overall you will win 5. So in this situation, you will again win 5 rupees. So in this situation, you will again draw the game, because 5 plus 5 is 10, and you have given 10 rupees for the entry fees. And this tail here, you will lose all your money. You lose minus 10. So you lose 10 rupees here, minus 10. Okay. Now if you see this 5, 5 and this 5. So you see this, there are these 3 possibilities. So winning of this 5 rupees. Let's suppose if I have to see how many possibilities are there for winning of this 5 rupees, let's say for this case, winning of 5 rupees, what's the probability? 1, 2 and 3, and all of these are mutually exclusive. So this is 3 by 8. So probability of this is 3 by 8. Okay. And what's the probability of this? Probability of winning 10. So you can see 1 by 8. Okay. So either you win this. So I'll mark these maybe with yellow. So here you win. Here you are winning. Here you are winning. Here you are winning. Here you are winning. Oops. Doing. So here you are also winning. So in 1, 2, 3 and 4 cases you are winning, if you see it. So you are winning 5 rupees, 5 rupees, 5 rupees and 10 rupees over here. So I am assigning probability to this win or lose. Yes, I think we have a question. Yes. Yes. So we had a mistake over here. So if you see in this situation, so this we are losing 5, then winning 5, then losing 10. That is overall we have lost 5. So then we have these 3 possibilities. So if you see, the possibility in winning is this. So either we can win 5 rupees or we can win 10 rupees. Okay. So in this case, 5 rupees over here. So wherever we can win 5 rupees. So this has 2 by 8 probability then. So this over here is having probability 2 by 8. Okay, and the winning 10 has probability 1 by 8. Now I'm assigning probabilities to these individual outcomes, and I know this winning this 5 rupees and winning this 10 rupees is mutually exclusive. So I can add these things together. So 2 by 8 plus 1 by 8 is again giving 3 by 8. Okay, directly I also said in the first case, I said the possibility is 2 by 8 because there are two scenarios where I can win. So that's 2 by 8 directly. So if you see this now, again you have to rearrange the probabilities from this, and then you can see you can add the probability from here. You can easily conclude that we will win with the probability of 2 by 8. The takeaway lesson is that the first thing, you should construct a sample space, and there are various ways of constructing a sample space. So once you construct the sample space, now you should assign probabilities to individual outcomes. Okay, so how to solve the problems? Now whenever you have a problem, so what you do is you construct a sample space. Once you have this sample space, so after that what you should do is assign probabilities to the individual outcomes, or to the individual outcomes. Okay, or maybe to the events. You can also assign probability to the events, and then see if these events are mutually exclusive. If they are, you will use inclusion. You will use directly additive axiom. If they are not, then you will use inclusion axiom. Then you'll have to decide, is these, let's suppose you have these favorable events, you want to add them up, or whatsoever you want to do is either you can use additivity axiom or inclusion exclusion based on the thing that there is. If there is an overlap, then you can use inclusion exclusion, or if there is not overlap, you can use the additivity axiom directly. Okay, how many of you at least got the notion how to now see the probability thing? So once you see a probability quotient, the first thing that you should pop in the head, okay, what are all possible outcomes? Okay, and maybe all possible outcomes if you have, then we'll see what are the favorable outcomes that I have. And then probably I can also use naive definition of probability, or I can use axiom probability, whatever it is. So but you should somehow construct a sample space. Okay, now we'll go to the easier questions, but you should always keep this approach in the mind. So now the question is, so let's suppose in an experiment in which let's suppose this, so we have two dice. So we have two dice. So dice basically means those things which have 6, which is a form of a cube, and it has 6 faces, and each face is numbered with 1, 2, 3 till 6. So now if you roll these two dice, what is the probability that sum of the two faces turned out to be 7? Okay, so what is this? Basically you are rolling a die and you are rolling two dice simultaneously, let's suppose, or you can roll one die twice. So in each of the experiment, now the question is, so what is the probability that once you see the face up die, when you see the die and you see its face up, so it can be one die can have 5 and other die can have 4, can have 2, something like this. Okay, this is number 5 and this is number 2, let's suppose. So in this case, the sum is 5 plus 2 is 7. Now the sum is 7. So now that means this is our favorable outcome. So now the question is, what is the probability that I will get this number 7 when I add the numbers that the two dice have on their top face? Can you calculate this? Pretty easy question. So this is the question. If two dice are rolled, what is the probability that sum of the upturned faces is equal to 7? Now these things are sometimes called as sequential experiments. So if you see, so usually how people solve it, they say, okay, I'm rolling two dice. So it can be thought of rolling one die and then rolling second die. So I have the possibility 1, 2, 3, 4, 5 and 6. And with this, I have again 6 possibilities. 1, 2, 3, 4, 4, 5 and 6, something like this. Okay, so for this I have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, something like this. You can either make this is called as tree diagram if you want to make these trees. Okay, so this is becoming a bit cluttery. So sometimes what you also do is you also make it like this. You also make a diagram like this. So it depends on what makes you visualize these comfortably. Okay, let's draw more of these. This is 1, 2, 3, 4 and 5. So this is 6. 1, 2, 3, 4, 5 and 6. One more. So what you can do, you can say 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5 and 6. So these are sequential experiments. So you can either use this tree diagram, so where you can draw a tree, or you can use this sort of checkers board. You can see this is 1, 1 possibility, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and accordingly fill all of these things. Okay, now if you again see this, so this is somewhat like arrays. So when we learned about arrays, I said how to visualize arrays. Either you can think them like array of arrays, you can make a tree over there. So if you have one array, you can think, okay, like this is my array. Okay, one array has again one more element, so this is like a tree method. Okay, and otherwise you can think these multi-dimensional arrays like this, like checkers. Okay, so now if you see this, as Asif rightly said, so we can make an assumption here. The first thing you should ask yourself, okay, these are the total 36 possible outcomes, but is it legit, or is it at least reasonable to make the assumption that all of these are equally likely? So here if you see, this is reasonable to make. So all of these are equally likely, so I'll say each of this outcome has probability 1 by 36. Okay, now I'll see how many are favorable in my favor. So in my favor, the possibilities which add up to 7 are the favorable event. So what are these? So I can just color them. So this is, let's suppose 2 and 5. Let's suppose this over here. Okay, 1 and 6, this over here. If you see these diagonal elements, okay, so this diagonal is my favorable diagonal. Okay, how many possibilities? 1, 2, 3, 4, 5 and 6 possibilities out of how many? 36 possibilities. So you can think area also as probability. You can think this probability as area now. So if this is the total area, so this is the area occupied by my favorable things. So sometimes you have to think it as area also. So it is very helpful intuition. So when you make these diagrams, you visualize these things, so you can think the probability as area. More the area, more the probability. So now you see the favorable area is this much. So this is 6 by 36. This is 1 by 6. Okay. So in this, what we learned is, if there is a possibility where you have the sequence of these, the sequence of experiments, so you can use this tree diagram. Okay, or you can use this checkers also, and then you can also think probability as an area. You'll see, okay, how much area is in my favor. Let's move to another question. Let's suppose you have to draw 3 balls randomly. Okay, so and then we have a bowl. So we have a bowl like this. Okay, something like this, in which we have 6 white balls. We have 6 white balls. So this is white, and we have 6 of them, 6 white balls. And then we have 5 black balls. So I'll write this as black balls. Consider this is black or blue balls, whatever. Let's consider them as blue balls. So you have 6 white balls, and then you have 5 blue balls. Now you are drawing 3 balls. Okay, you are drawing randomly these 3 balls. So what's the probability that one of these balls is white and other 2 are black? So the possibility that one is white and other 2 are, let's suppose, blue, not black, blue. Okay, so you have to calculate the probability of this. Now if you see this, so the first thing is, we should see if we have 11 balls. So we have to draw 3 balls randomly out of it. So Arshan mentioned it. So should we see if order matters or if order does not matter here? So you can do the question in both the cases. Order can matter or cannot matter. So what we do is, initially we'll see if order matters. Basically order matters, that means we have to see permutation. So how many permutations are possible then? So you have to have 3 balls. So 1, 2 and 3. So initially you have 11 multiplied by 10 multiplied by 9. These many number of permutations. That is I think 990. Is it? I think so. So 990 possibilities. So this is total number of possibilities if you draw these balls and where order matters. Okay, so this is the possibility. Okay, how many of them are favorable? Now the order matters. Okay, so the favorable is this: white, blue, blue. This is one favorable. Then we have blue, white, blue. This is also favorable. Blue, blue, white. This is also favorable. So these 3 things are favorable. Okay, so for this thing, let's suppose for this, for each of these, the possibilities is 1, 2 and 3. So you have to, now out of these white balls, okay, what you have to do is you have 6 into 5 into 4. If you see this, okay, so there are 6 multiplied by 5 multiplied by 4 outcomes. Okay, so why? Because you will have to construct this. You have to take one ball from the from 6 white balls. So I am saying, okay, there are 6 possibilities, and the other 2 are blue balls. Okay, irrespective, but because there is a symmetry in the problem. Okay, there is a symmetry. If you see this, so there is symmetry in the problem. So each of these have 6 into 5 into 4 possibilities, and multiplied by 3 because there are 3. So this is 6, 5, 34, and this I think 120. So we have 120 multiplied by 3 divided by 990. This is when order does not matter. So what I said is, when order does not matter, the first thing is the total possible outcome. So how many are there? So you have to draw 3 balls, and you have total number 11 balls. So what you can do is 11, 10 and 9, basic permutation, or you can say 11 PR, 11 P3, something like that, and this results to this. I am not using formulas on purpose because I don't want you to mechanically know this. I want you to reason it from first principles. So you have to draw 3 balls out of 11 balls. So you have these 3 places to fill. You are saying that for the first ball 11 possibilities, for the second ball 10 possibilities, for third ball 9 possibilities. So in total you have 990 possibilities. This is the total number of possibilities total. And now I said, because the order matters here, so I said there are 3 possible orders. So all of these are favorable to us. WBB, BWB, BBW. Okay, and this is symmetry. If I just compute for one, probability of 1, so I can multiply it by 3. So just getting 1 ball out of 6 balls, so it has 6 possibilities. Now if you see, this is a multiplication rule happening, and then you have to pick a blue ball, or maybe whatever you said, black or blue ball. So the possibility of that, because we are in total we have 5 balls, so you took 1 ball, the first ball has possibility 5 and the second ball has possibility 4. That is 6 multiplied by 5 multiplied by 4, then that means 120. So 120 multiplied by 3, so this is 360 divided by 990, and this is 4 by 11. So how many of you are able to understand this? So how many of you were able to understand this? The second case is where order does not matter. Order does not matter. Now we'll see order does not matter. So if the order does not matter, what we will do is we basically go to permutations. Okay, so there we have the total number of permutations possible is 11C3. These are the number of permutations. Now order does not matter. So what we have is, you have this blue and white. Order does not matter for us. So you have to basically, now you have 2 things. So the first thing is pick up a white ball from 6 white balls. Okay, so how many possibilities? So the possibilities that we have is 6C1. Okay, and in the second case, you have to pick 2 balls of color blue. Out of how many balls? Out of 5 balls. So if you solve this, again this will be 4 by 11. Okay, now you see number of possibilities also decrease, but number of favorable outcomes also decrease in the similar proportion. Okay, that's what I said. In such problems, you can use permutations as well as combinations, but you have to be careful that if you use permutation or combination, you should not overcount the things. So if you are using, in the first case, you are saying total number of possible outcomes, you are using permutation for that. Also in the favorable outcomes, C, I am using permutations, and vice versa. If you are using combinations, use the combinations in here. Okay, this is the same thing. So in here, the total possible combinations, I can pick 3 balls out of 11 balls, total number of combinations. Okay, and now you have to see total number of combinations. Now there are 2 things. You have to pick up 1 white ball and you have to pick up 2 blue balls out of 5 and out of 6. Okay, I hope this also gets clear. Okay, now the takeaway from this question was, if you use permutation or combination, so you have to accordingly tune your calculations. So in total outcomes, if you use without order, so in the favorable also use without order. So in if you use with order or why order matters, so in both of these favorable case as a total case, you should use this. Now let's go to this. Now let's see a question. The question goes like this: if you have 10 couples, okay, you have 10 couples in a party, let's suppose, wherever they are. Okay, you have 10 couples. So what you basically do is, you are randomly selecting 5 people. Out of these 10 people, 10 couples, you are randomly selecting 5 people. So now you have to tell me, what is the probability that these 5 chosen people are unrelated? They are unrelated. By that I mean, nobody among them should be married. So you basically are taking, so it is the question like this: you have 10 of these pairs, so you are taking one from this, so you are taking some other pairs, and these 5 people are not related to each other. Okay, no couple is basically selected, among those. Is this question clear? The question we had is, we had 10 couples and 5 people were randomly selected. That means we had 20 people. So out of these 20 people, 5 people were randomly selected, and we have to calculate the probability that all of these are unrelated. These 5 people are unrelated that selected. The first approach could be like this. So you have to choose 5 couples, 1, 2, 3, 4 and 5. The 5 people are selected. So first we will calculate total outcomes, total possibilities. Total possibilities will be, so if I choose 20 people, then I can choose 19, 18, 17 and 16. Okay, so this is my total possibilities, because I am filling these 5 places that I have. I am filling 5 places and I am considering the order matters here. So these are total possibilities that we have. Once we have this, so now we have to again see the favorable possibilities. That means we have to select for the first position. Let's suppose we have these 10 couples now. I have 10 couples. So if I select one person from from this group, that reduces my possibility. Now I actually had 20 people. So when I selected one, so let's say I selected husband. So I cannot select the corresponding wife. I can't select that. So that means each way when I'm making a decision, I'm losing two possibilities. That means over here, if I have, let's say, 20 people I can select, in the second step when I take second decision, I only have 18 people, because one I selected, other I had to reject. Why? Because I cannot select it, because I'm calculating the probability that these two people are unrelated. Similarly, because of this I rejected two people, because of this I rejected two more people. Now I'm left with 16 people, so I can choose one among those 16. So once I choose one among those 16, now the possibility again reduced to 14, and possibility here again reduced to 12, something like this. So this is my favorable and this is my total, and I can assume that all of these are equally likely. I can divide them together. Okay, that means and the second possibility I said you can think it without order also. So how I can do it without order? So I can choose let's suppose from how many couples I had, let's say these 20 people, so 20 out of 5. So these many combinations are possible. I have to choose 5 people among 20. Okay, these many of total combinations. This is total combinations. Now if you see, if I can think of the problem like this. Now I have these 10 couples. Okay, I have these 10 couples. So I'll choose 10, 5. That means I'll choose 5 couples among these 10 couples. That's the first thing. So I'll choose any 5. Okay, I'm choosing any 5 of these. So how many combinations are possible? These many combinations. I'm choosing couples now. Okay, then once I choose couples, then the second thing is, out of these couples now I have to choose a person. Okay, that's the second possibility. So this is ways in which I can select 5 couples. The second thing is, once I chose the couples, then I have to see, okay, which among these two can I select? So how many are these then? So we have 5 places to fill. So in the first place I can choose husband or wife, then husband or wife. So how many possibilities? That is 2 to the power 5 possibilities there. The first experiment was to choose a couple. So I chose 5 couples out of 10 couples. So these many number of ways are there. And then the second experiment was, now once I chose the couples, then I have to select which one should I select among those two, husband or wife. So there are 5 places to fill. The total number of possibilities then are 2 to the power 5. So this is the total probability. Okay, this is the probability of we choosing 5 people, and each of these are unrelated. Okay, one more question. So let's suppose we have n balls. This is question. So we have an let's suppose an urn, or we have, let's suppose, a bowl in which we have n balls. So in that bowl we have n balls, and out of which one ball is special. So one ball is special. So we have n balls, and out of n balls just one ball is special. Okay, so if we draw k balls from this, so if k balls are drawn from this, if we take k balls out of this, okay, and one ball is drawn each time, so k balls are drawn one at a time, so will each selection be equally likely? So okay, we can select any out of n balls, so each of these balls have equal probability of coming out. Okay, so tell me, what is the probability that special ball is chosen? Probability that special ball is chosen. Again, to read the question, an urn contains n balls, in which one of the ball is special. If k of these balls are withdrawn one at a time, okay, with each selection being equally likely to any of the balls, okay, that time at a time. So what is the probability that special ball is chosen? So if you see this problem, how this can be solved now. So I said we had n balls, we are drawing k balls out of it, and one ball is special. Okay, one ball is special. So in order to dissect the problem, that means n minus 1 balls are not special. Okay, so now I am saying total, how many total possibilities are there? So that is quite easy. You choose k balls out of n balls. Okay, and this is our total number of combinations possible. Now we have to see how many favorable are there. So the favorable is, I'll choose my special ball and others can be non-special. I'll choose one ball which is special and others can be non-special. So what I'm saying is, so to choose this one ball, because there's only one ball, there's only one possibility. Or I can say one choose one, like this, one choose one, or I can just say one ball. The second thing is, I'll have to choose other k minus 1 balls from other n minus 1 non-special balls. So I can say n minus 1 choose k minus 1. Okay, so this is the probability that our special ball gets chosen. Or the second thing is, I can introduce more notation. What I can say is, I can say, let's suppose AI. This AI is ith ball is special. Ith ball is special. If I say something like this, I'm making an event on purpose. I'm saying let's consider ith ball is special. If I say I1, that means the first ball is special. 1, 2, 3, this is special ball. So till n. If I say A2, A2 basically means 1, 2, second ball is special. Third, something like this. Okay, so we are saying this. So AI denotes the event that is special ball is the ith ball. A1 means first ball is special. A2 is second ball is special. Okay, now the thing is we can do it like this. So we know that probability of A of I is 1 by k. This should be k actually. So we are choosing k balls. Okay, if we are choosing k balls, that means any ball can be special out of these k balls. Okay, that's why we said everything has equal probability. So probability of AI, probability of A1 is 1 by k. Okay, probability of A2 is also 1 by k. And all of these events are mutually exclusive. So I can say the probability of ball is special basically is union of probability of AI. I goes from 1 to k. Okay, so I chose 1 can be special, 2 can be special, 3 can be special, or k can be special. So I know what is the probability of this. So the probability of AI, okay, so this is basically summation of probability of AI. I goes from 1 to k. So we know that summation of I goes from 1 to k. So this is 1 by k. I goes from this. So this should be equal to, we have n divided by k. Oh, sorry, k divided by, it should be k divided by n. K by n. Because you have to add all of these things. So this should be k by n. So this is 1 to k. I'm saying probability of AI should be 1 by k. So each of this has probability of this. So this means k divided by n. Total probability is k by n. So I think here we made a mistake. This should be 1 by n. Probability a ball can be special is 1 by n because we have n balls. Okay. The probability of ith ball being special is 1 by n because out of n balls, any ball can be special. That's what it said. Any ball can be special. So out of these, if first ball is special, it has probability 1 by n because n balls are in total. Okay, so that boils down to this. This is k by n. The first thing that we said is we can use this approach. So you are choosing k balls out of n. Then you think it in this direction. Otherwise, you can say, let us call this AI as ith ball being special. So that means probability of AI is 1 by n. Why 1 by n? Because n balls are there. We are saying 1 is special. So if I say 1 ball is special, each ball is equal likely to be special. That is 1 by n. And if I am performing an experiment like this, so this is rightly n. So 1, 2, 3, 4. So here 1 is special, 2 is special. A3 means 3 is special. So now all of these events are mutually exclusive. So I can use this. So if I can use summation. If I can use this, I can directly say this is k by n. So I'll close this session with one very good example that is called as matching problem. Matching problem. Okay, this was actually a game. So let's suppose you have n cards. Understand the game. You have n cards. So in n cards, they are numbered from 1 to n. So they are numbered from 1 to n. This is 1, 2, 3 until n. These cards, we have a deck of cards, and these deck of cards are numbered from 1 to n. So this card is shuffled. This is well shuffled. So if you shuffle these cards, now the thing is, now what you will do is you will basically check these cards one by one. So let's suppose when you shuffle it, the first card can be 3, second card can be 8, third card can be 4. So now the question is, why is it called matching problem? I actually want to find the probability that nth card or maybe kth card is k. Kth card is k because you shuffle it. So if let's suppose if I choose first card, it was 10. If I choose second card, it was 14, 89, something. So if I let's suppose chose some kth card, okay, when after the shuffling, so if it came out to be k, then I'll win the game. Okay, it is something like this. If I am playing this in casino, if I have let's suppose some 50 cards, number from 1 to 50, so I will shuffle the whole cards. So I can bet my let's suppose $5. $5 if I'll win, I'll make it double, or I'll let's suppose triple the amount if some card exactly came at its place. Okay, this is called a problem of derangements. So that at least one card is in its own place. So if it was at kth place, it is still at kth place after all the shuffling. Okay, so what is the probability of winning? So what is the probability of this happening? That at least one card will be at its place even after shuffling. So the probability of winning. So when will you win? So if at least one card is in the same sequence as it was, let's say 10th card is at the 10th sequence, and let's say 50th card is at 50th place, something like this. So can you do this question? Or this can be thought in another way. So people sometimes also give the question like this: the people are coming into the party and everybody is wearing some hat and they are throwing the hats. They are throwing the hats. And what is the probability that at least one person will get their own hat back? So they are then picking up randomly the hats. So we have people, and people are throwing the hats randomly. Okay. So once this is over, they are picking up the hats. Okay, they are picking up these hats. So what is the probability that at least one person will get its own hat? Okay, both of these is same problem. So one is a card game and second is again a hat problem. So in both of the cases you have to calculate probability that the kth thing will be at the kth place, at least one of them, and maybe one is at one place, two can be at two place, three can be at three place. So here you again have to construct sample space, see all the possibilities, and this might turn out to be a bit tedious. You'll have to think. So this is the homework, and in the next session we'll start with this problem and then we'll go to the conditional probability. So here I'll stop recording, I'll stop torturing you people, and I'll meet you in the next session. Before that, if you have any questions, you can ask me.